Okay, welcome. So in this short video, we are going to be solving the following question, which was requested from me by one of the students. So here, I would like to find the equations of motion for this mass system here. It is in one of the problem sets. It's the problem set 1, and it is also the question 2, I think. So there is also a force applied onto the second mass here. So this is an accelerometer here, and it can understand where the direction of gravity is, or when you shake it, it actually can give you the amount of acceleration you apply to this casing by moving it in that way. So here I would like to find the equations of motion for both of the masses here. So here is what I'm going to do. So our modeling always starts with two equations and 1 times x1 double dot. This is going to be the net force applied onto the first mass, and the second equation I have m2 times x2 double dot, and this is going to be the net force applied onto the second mass. So here is what I'm going to do. So suppose that I fix one of the masses here. So since trying to write the equations of motion for both of the masses at the same time is difficult, when I try to write the equation for m1, I'm first going to be fixing m2, and then when I'm trying to write the equation for m2, I'm going to be fixing m1, okay? So now let us try to write the equation for m1. So you see that in m1 there is no external force like the case in m2. So here, in order to be able to write the right-hand side here, I need to count the forces that are applied onto m1 by the other elements in the system, like this frictions or this k1 and k2, etc. So here, what I would like to do first is that I'm going to assume that m2 is fixed. So I'm not going to write the second equation first. So let me first assume that x2 is equal to 0. Okay? Suppose that I don't move m2 at all. Okay? In that case, this is fixed. And in order to be able to write the right-hand side of this equation, then here is what I'm going to do. Suppose that I move m1 a little bit to the right. Okay? So what does this mean? This means that I take an x1 which is positive. So suppose that when m2 is fixed, I move m1 a little bit to the right from its equilibrium position, so that x1 becomes positive. Okay? Then let me think about the forces applied onto m1 by the outside elements. So what happens when I move m1 towards the right just a little bit? I see that in that case this spring is going to be squeezed. So since this spring is squeezed, then it's going to, since m2 is fixed, it is going to try to push m1 backwards to the left. Okay? Spring is going to be squeezed, and it's going to push m1 back towards the left. So that force is going to be in the negative direction of x1. Okay? That means that what I have to do here is to write minus k1, k2 due to this spring here, minus k2 x2 here. Okay? So this is only the force due to the spring k2. Okay? So sorry, this is going to be x1, of course. Okay? So here x1 is positive and k2 is positive, so minus k2 x1 becomes a negative force. And what does a negative force mean? It means a force in the opposite direction of increasing x1. note that in such an equation, I need to always count the forces applied onto M1 in the direction of increasing x1. Increasing x1 is in that direction, and therefore this means that if I have a force in the opposite direction, I need to write here a negative force for positive x1. Okay, x1 is positive, k2 is positive. I put here a negative sign. This makes the force applied onto the mass m1 in the direction of increasing x1, a negative force. Okay, that means a force in the opposite direction of increasing x1. Okay, what about the first spring? In the first spring, when I pull the mass from here to here, this first spring is expanded, it's enlarged, okay? So then this spring, since M2 is fixed, this mass is now fixed, what happens is that when I pull the mass to the right, this spring is expanded and it again pulls the mass back towards the left, okay? That means that I need to put here minus K1 times X1, okay? This is true when, so this part of the equations are true if x2 is equal to 0, okay? So these two should be the equations of motion when x2 is equal to 0, okay? What happens, for example, if I pull the mass, so suppose that x2 is not equal to 0, suppose that if I move the second mass as well with the same amount as I move the first mass. Maybe I should draw it a little bit better. Suppose that I pull the both masses towards the right just a little bit, but with the same amount, okay? Suppose that x1 and x2 are both positive, and suppose that I move x1 and x2 to the right with the same amount. In that case, what should be the force applied onto M1? In that case, this end of the spring and the end of the spring here moves with the same amount to the new position. So this spring is neither squeezed nor it is expanded from its equilibrium position. Similarly, this spring, it is this side and this side moves with the same amount to the right, and there is no expansion or squeezing of the spring anymore. Okay? That means that if x1 and x2 are actually equal, on the right hand side here I need to have 0 forces due to the springs, because in that case the springs are neither squeezed nor expanded. That means that I need to have on the right hand side 0 forces when x2 is equal to x1. Okay? So how can I ensure that is the case? I can just ensure that by putting here x1 minus x2 and x1 minus x2. So in this case, when x1 is equal to x2, when both of the masses would be moved with the same amount to the right, no force is applied to x1 at all. Okay? And also here it satisfies when x2 is equal to 0, I would have here the forces that are required by the springs. So now I would write the force. So this completes actually the forces that are written due to the springs. So now suppose that I would like to write the forces due to the friction elements here, B1 and B2. I would like you to suppose again x1 and x2 is equal to 0. Suppose that this mass, the second mass, the outer case here, is stationary. Suppose that I fix it there where it is at x2 equals to 0, and suppose that I move only m1. Okay? Suppose that I now keep x1 dot, x1, suppose that I move the mass to the right, towards the right. Okay? That means that x1 dot is positive. I move the mass to the right with constant velocity when the second mass, this mass, is fixed there, where it is, at x2 equals to 0. So when this mass is fixed, and when I move m1 to the right with constant positive velocity to the right, these frictions will be effective, okay? And since the second mass is stationary, there would be friction forces in that direction towards the left trying to stop this mass. So I would have minus b1 x1 dot here and minus b2 x1 dot here. Okay? These are the friction forces due to these two friction elements here, or these two friction phenomena here, when I fix the mass x2 at 0, when I move only m1 towards the right. Okay? So now I want you to ask yourselves the question, what happens if I move both of the masses with the same velocity? Okay? In that case, mass m1 would not move relative to the mass m2. So the mass m1 would be stationary inside the mass m2. It would be stationary with respect to m2, although both of them are moving. Suppose that both of the masses are moving with the same velocity. In that case, the friction is not going to be effective at all, because there won't be any relative motion between these masses when we have both of the masses moving with the same velocity. Okay? That means that when both of the masses move with the same velocity, the friction forces that I have here needs to be equal to 0. That is why I need to put here just x2 dot, so that when the velocities of the masses are equal, there shouldn't be any friction force coming from b1 and b2 elements. Okay? Now this actually completes the equation for m1. So now I would like to also mention about the effect of the case when x1 is equal to 0. Suppose that x1 is equal to 0, okay? In that case, what happens to these equations? In that case, this equation turns into m1 x1 double dot is equal to, in that case, I would have, this is going to be minus k1 times minus x2. This becomes k plus k1 x2. Okay? And similarly, if x1 is equal to 0, then this becomes plus k2 x2. Okay? This is only when x1 is equal to 0. So now suppose that I keep this mass fixed. Okay? Suppose that x1 is equal to 0, and suppose that I move only m2 towards the right. Okay? I would like to check the correctness of the equation. So when m1 is fixed, when m2 is moved to the right, this spring is expanded and this spring is squeezed. Okay? Because this end of the mass 2 is coming to here, and this end of the mass is coming here, while m1 is fixed. When m1 is fixed, when I move m2 to the right, this spring is going to be expanded and this spring is going to be squeezed. It's the reverse situation is happening here, as in the other case, reverse situation compared to the earlier case when we keep m2 fixed and when we change m1 only. So when m1 is fixed and when m2 is changed, this spring is expanded and this spring is squeezed. And what about the forces? There would be a force, because this spring is expanded onto m1, it is going to pull m1 towards the right. That is just this force, k1 x2. x2 is positive because I moved m2 to the right with a positive amount. I multiply it with k1, then this becomes a positive force, which is in the direction of increasing x. Okay? So I have a positive force. And what about the other spring? The other spring is squeezed when I move this to the right, the outer case to the right. This spring is going to be squeezed, and mass m1 is going to be pushed by this squeezed spring to the right. Okay? So that is just this effect, plus k2 x2. Okay? So you see in this equation, I have both of these effects. When x2 is equal to 0, we have the effect of moving x1. When x1 is equal to 0, we have the effect of x2, as in these two cases. And what about the spring effects? What about the friction effects? When I do not, suppose that I don't move, suppose that x1 dot is also equal to 0. Suppose that I don't move m1 at all, but suppose I move only the outer case towards the right with fixed velocity. This is fixed, and this is moved to the right with fixed velocity. Then due to this friction, when I try to push the outer case, it is going to try to move the inside mass as well. So there will be a friction force applied onto m1 towards the right when I move m2 towards the right, and when I fix m1 at its current position. Suppose that I don't move m1 at all, and suppose I move m2 with fixed velocity to the right. And in that case, due to the friction, this m1 is staying here, and I'm moving the outer case. So due to the friction between the outer case and the mass, this mass is going to want to go towards the right due to the friction forces. Just like this case, this is m1. If I push this second mass to the right, then it's going to push the first mass to the right as well. Okay? So here, if I add the effect x1 dot is equal to 0, it is stationary, and minus is going to cancel, and I have plus b1 x2 dot. If x2 dot is positive, when this mass is stationary, if x2 dot is positive, meaning that this outer mass is going towards right with positive velocity, on m1 there will be a force pulling it towards the right. Okay? And this is a positive force, b1 positive, x2 dot is positive, and I would have a plus sign in front. Plus b2 x2 dot. Okay? The other friction is going to behave in a similar way. So this is only the case when x1 and x1 dot is positive. In such a case, I have all positive forces due to the motion of the outer mass. Okay? And in the earlier case, if x2 is equal to 0 and x2 dot is equal to 0, in that case, I keep this mass where it is. But I move m1, and if I move m1 to the right, I get just these equations, minus k1 x1, minus k2 x1, etc. Okay? And in these cases, you would have the equation m1 x1 double dot is minus k1 x1, minus k2 x1, minus b1 x1 dot, minus b2 x1 dot. Okay? So these are the cases when one of the masses are stationary. If you want to combine these two equations, so if none of the masses are stationary, then it is going to be this equation which is going to be correct. Okay? So now let us write the equation for the second mass. m2 x2 double dot. Okay? Now I need to write the forces applied onto m2 in the direction of increasing x2. Okay? On the right hand side, I need to count the forces applied onto m2 in the direction of increasing x2. there is such a force on this mass and it's applied from the outside, which is F. And then I'm going to be doing the same thing over and over. Suppose that I fix M1, okay? Suppose that M1 is fixed. What does it mean? If M1 is fixed, then X1 is equal to 0 and X1 dot is equal to 0. If M1 is fixed, then what is going to be the force applied onto M2 by the outside element when I fix M1? Suppose that when I fix M1, suppose that I move M2 to the right just a little bit. So I make X2 positive, okay? And in that case, this spring is going to be expanded, and since M1 is fixed, this spring is going to pull M2 towards the left, okay? Towards the left means that it is the opposite direction of increasing X2. Therefore, the force applied by K2 onto M2 would be minus K2 X2, okay? Still, suppose that I have still M1 fixed and I move M2 to the right with a positive X2. In that case, this spring is going to be squeezed, and since M1 is fixed, a squeezed spring is going to pull or push M2 towards the left, okay? And that is again the negative direction of the force. So I have minus K1 X2 here. Okay? These are the effects of X1, these are the effects of K1 and K2. And now suppose that I want to include the effects of the friction. This mass is fixed. I am moving M2 to the right with a fixed velocity X2 dot. In that case, due to this friction, this outer case will actually experience a friction force trying to stop itself, okay? So the friction force is going to be pulling the mass back towards the left. Similarly, this friction force, when M1 is fixed, when M2 is moved in that direction, would be pulling the mass M2 towards the left. That means that the effects of B1 and B2 would be added like minus B1 X2 dot minus B2 X2 dot. Okay? So these are the cases when I have X1 is equal to 0 and X1 dot is equal to 0. When this mass is fixed where it is, I would have these equations. But what about at the same time M1 is moving, when this is moving at the same time as M2? If the displacements of M1 and M2 are the same, then these springs will be neither squeezed nor expanded. Therefore, the forces due to the springs applied onto M2 should be equal to 0 when the displacements of M1 and M2 are the same. That means that I need to here subtract X1 from these spring forces, so that when the displacements of X1 and X2, M1 and M2 are equal, there is not going to be any spring force on the right. Okay? Similarly, when the velocities of the masses are the same, these masses won't move with respect to each other at all. If two things are going with the same velocity, then those two things do not move at all with respect to each other. Okay? That means that these friction forces should disappear when the masses have the same velocity. So I need to subtract here minus X1 dot to actually take care of that fact. When the velocities are equal, then there won't be any friction force, because these two masses then won't move with respect to each other. If two masses have the same velocity with respect to each other, then if if two masses have the same velocity with respect to the ground, then they won't move with respect to each other at all. Only if they have different velocities, they are going to scratch each other, or they are going to move with respect to each other, causing a friction force. Okay? That is why we have this type of equation. So then I have these two equations. This is my first equation, and this is the second equation. So when you actually combine these two, or we can apply some algebra onto these equations to write the following. M1 x1 double dot, I can actually collect x1 terms, x1 minus x2 terms here, to write minus k1 plus k2, x1 minus x2. And I can also collect x1 dot minus x2 dot terms, write minus b1 plus b2, x1 dot minus x2 dot. This is my first equation, and the second equation becomes similar. M2 x2 double dot is equal to minus k1 plus k2, x2 minus x1, minus b1 plus b2, and I would have x2 dot minus x1 dot. Okay? So I have these two equivalent equations here. But what are these equations? So if instead of having such a complicated system, if I only have the following simpler system, I would get exactly the same equations. Okay? So if I had M2 here, and if I had M1 here, then suppose that I have a friction between these two masses, which is B1 plus B2, and suppose that I have a spring force between these two masses. I have the spring coefficient K1 plus K2, and I apply F to the same mass and the second mass, and I have, in this case, this is the displacement of x2, and this is the displacement of x1. In that case, if I have such a system, I would get exactly the same equations as this more complicated system here. Okay? So in this case, everything looks simpler. If I want to write the equation, so when I try to write the equations, I generally try to fix one of the masses and then write the equations for the other mass. And when I try to write the equation for this one, I fix this mass and I try to write the equation using that method. So when you try to write the equations for the masses in this way, this method might be useful. Try to fix one of the masses and try to move the other one. Then the equations would be simpler, and then you would try to think about the relative motions. If both of the masses are moved with the same amount, then the springs won't be effective anymore. And if both of the masses move with the same velocity, then the friction would not be effective. So then these forces should actually disappear. So here, if you would like to, so when you actually look at these equations, you can actually see a trend. If I would like to write the equation for M1 x1, in that case, if I put here these minus signs, it is always going to be the own variable of the mass that is going to appear here in the relative motions. Okay? When I try to write M1 x1 double dot, if I put minus signs everywhere on the right, then in the relative motions, it is always going to be the own variable of the mass that is going to appear first. So you see here that x1 appears first, x1 appears first, x1 dot appears first, and x1 dot appears first. Similarly, when I try to write m2 x2 double dot, on the right hand side, if I put minus signs everywhere here, it is always going to be the variable related to x2 that is going to appear first. x2 appears here, x2 appears here, x2 dot and x2 dot. Okay? So, for example, what would happen if I added another friction here? Okay? B3. Where would I change those equations? Or how would I change those equations? So in that case, I wouldn't really change at all the equation for M1, because this friction is between M2 and the ground. Okay? This friction is between M2 and the ground. So this equation then would remain the same, because there is nothing affecting this M1, there is no effect of this B3 on this M1 directly. Okay? The effect of this friction appears on M1 only through M2. Okay? Therefore, M1 equation really will not contain anything related to B3. B3 is only going to appear in the equation of M2 there. Okay? And what would be the change that I would make to this equation? So think about the same thing. If I move M2 towards the right with fixed velocity, then the friction between the ground and this M2 would pull the mass towards the right. Okay? And the effect of the friction would come here like this, B3 x2 dot. Okay? And should I subtract x1 dot from here? No, I won't subtract it, because this friction is not between M1 and M2. This friction is between M2 and the ground. So the only term that I need to add here is minus B3 x2 dot. Okay? And you see here, when I try to write the equation for M2, when I put a minus sign here, it is the own variable of the mass that is appearing, which is x2 dot. All right? So there is always a consistency with these equations. And the shortcut is, if you put minus signs, it is always the variable of the mass that is going to appear first. When you put minus signs, it is always the variable of the mass that are going to appear here. Okay? That's all for this solution. Thank you very much for watching. Bye-bye.